Assalamualaikum warahmatullahi wabarakatuh. My name is Dimas Aryasatya, and today I will be giving a short presentation on thermochromic materials. Here are the table of contents. So what is thermochromic materials? So first and foremost, a chromic material are materials that undergo various color changes through alteration of electron density of a substance caused by external stimuli. And in this case, for the thermochromic materials, the external stimuli is associated with heat. So for the properties of the thermochromic materials is the color change, the adjustable transition of the color change, the response time of the color change, the durability of the material, and also the safety of the material. So for the history of the thermochromic materials, scientists like Johann Heinrich Lambert and also Robert Boyle documented observations of materials exhibiting color changes with temperature. For instance, Lambert noted the thermochromic behavior of certain minerals in the 18th century. In this period, it saw the isolation and experimentation with specific compounds showcasing thermochromic properties. These early efforts laid the groundwork for future advancements. So for the timeline, in the 1800s, scientists began isolating and experimenting with compounds that displayed thermochromic properties. In the 1960s and 70s, the focus shifts towards practical applications, and thermochromic pigments found their way into novelty items such as mood rings. And then in the 80s and 90s, research intensifies on developing thermochromic materials for a more functional purpose, such as temperature indicators in food packaging. And from the 90s until now, the advancements continues, and researchers explore incorporating thermochromic properties into paints, coatings, and other materials for various industries. So for the principle of the thermochromic material is the molecular structural change. So the molecular structure of the thermochromic materials are susceptible to temperature change. And this temperature change will cause them to undergo a visual switching of color. And intermolecular hydrogen bonds form as a result of the pi-electron coupling between the acid and the base centers, such as conjugate acid donates a proton to the conjugate base, leading to molecular structural changes. A shift-based compounds undergo thermochromism due to tautomerism. For example, crystalline and salicylidene-2 aminopyridine derivatives are shift-based compounds that switches from the enol tautomer to the cis-keto tautomer as protons transfer from the oxygen atoms on OH to the nitrogen atoms. There is a temperature-sensitive equilibrium between the two forms. So the mechanism of the color change. The fundamental of thermochromism is the change of color due to fluctuation of temperature. The color change in thermochromic materials is primarily driven by structural alterations triggered by temperature variations. These alterations affect how material interacts with light, ultimately influencing the perceived color. So for organic thermochromic materials, they are usually available as three component system consisting of a color former, a developer, and then a co-solvent. This system produces a color change when the co-solvent melts, leading to the destruction of the dye developer complex associated with the loss of color. So the color former is an electron donating compound. The developer is an electron acceptor, and the co-solvent are usually the long chain of alkyl alcohols, esters, or acids. So here we can see the phenomena of ring closing and ring opening from a crystal violet lactone, CVL. The spiropyran form of the left and the merocyanine form on the right displays a blue color. This happens due to the increase of polarity through introduction of proton. For the inorganic salts have been used in thermochromic cancers such as manganese violet pigments. The pigment changes from dark violet to grayish yellow green at temperatures above 400 degrees. That this changes is due to the evaporation of water and liberation of ammonia from the pigment particles. COMO04 polymorphs exhibit optical contrast at the first order phase transition from a low temperature reddish brown gamma phase, CO5 polyhedra, elongated octahedral CO06 polyhedra, and MO04 tetrahedral. It undergoes a pseudo-reconstructive phase transition to the gamma phase, which is composed only of CO06 and MO06 octahedral. CR203, Al203 pigments display a wide range of colors varying from pink to red to purple and to chestnut red. depending on the L3 and CR3 substitution in the crystalline networks. So here we can see the difference in colors according to the temperature for the CVL, for the manganese, for manganese pigment. So the dehydration process occurred between room temperature and 370 degrees, and above 370 degrees, the violet color started to diminish, and the white color appeared partially on the surface of the pigment particles. At 410 degrees, the color of the pigment completely changed from violet into grayish yellow. This was an irreversible reaction associated with both evaporation of water and the liberation of ammonia from the pigment particles. And the last one is the polymeric mechanism of color change. So cholesteric and conjugated liquid crystalline polymers with a chiral molecular structure form a helical complexes which make them optically active. They express a Bragg's reflection type of thermoresponsive effect on exposure to visible light. Manipulation of pitch length of this formation by varying the temperature determines the color and thus make them useful for many sensing applications. When light hits a polymeric thermochromic material, a certain wavelengths are absorbed and others are reflected. The wavelengths that are reflected determines the color of the material. So here we can see a polymeric thermochromic material incorporate a special molecules that changes their shape and or arrangements when heated. This change in structure alters how light interacts with the material. As you can see in the picture above, the left and the right have different colors and different structures when the temperature is increased. So the types of thermochromism. The first one is the reversible thermochromic materials. There are two. First one is inorganic. The inorganic materials include metal alloys, metal chloride, which has the privilege of good temperature resistance, light resistance, and durability. The mechanism of discoloration of these kinds of materials is especially due to the change of crystal lattice, crystal water, and ligand geometry of the compound. And for the organic reversible thermochromic materials are distinguished by low discoloration temperature, low cost, and adjustable colors. The discoloration of organic materials is mainly related to their electron transfer, proton transfer, pH value, dimensional structure, electron spin, and etc. The second type is the irreversible thermochromic materials. Irreversible thermochromic materials are a type of thermochromic material that undergo a permanent color change when exposed to a specific temperature threshold. Irreversible thermochromic materials often contain compounds that undergo a chemical change at a specific temperature. This change could involve decomposition, formation of a new compound, or irreversible shift in molecular structure. So here I will be explaining about some types of the thermochromic materials. The first one is leucodyes. The leucodye is used in a wide range of applications. Some product is printed with leucodye. Thermochromic inks change from one color to another. Rather than transitioning from color to clear, it changes from one color to other color. For example, as you can see on the picture on the right, the spoon, the first spoon on the left, it is colored pink, but then it changes into a bit violetish. This phenomenon is achieved with an ink that combines a leucodye with a permanent colored ink formulation. For example, the ink manufacturer may formulate a green ink by adding a blue leucodye to a yellow ink. In its cool state, the printed ink layer is green, and once warmed, it refers to yellow, and as the leucodye becomes clear or translucent. Leucodyes can be designed to change color at various temperatures ranges, from as low as -25 degrees up to 66 degrees. In order to function, a leucodye requires a combination of chemicals working together in a system. The special system of materials needs to be protected from the components of the ink to which it is being added. So it is micro-encapsulated. The micro-encapsulation process takes a small droplet of the leucodye and coats as a protective wall around it. The leucodye microcapsules contain the complete color-changing thermochromic system, which when added into inks, give them their color-changing properties. And as you can see, there are two forms, the leuco form and the color form. When it is in the leuco form, it is transparent. It is fully transparent, and when you give UVA and heat in increase of temperature, it will change into the color form. The second type is liquid crystal. Thermochromic liquid crystals are complex, optically active thermotropic organic materials that exhibit an intermediate phase or mesophase between the crystalline solid and liquid phases. Liquid crystals can be classified into various categories depending on their morphological and optical properties. The three distinct categories of the thermotropic liquids crystals are osmotic, nematic, and chiral nematic or chiral nematic. The categories are determined by the degree and nature of the molecular ordering and orientation. The osmotic phase is the most solid-like among the liquid crystal modifications due to the molecular aggregates being oriented parallel to each other in two-dimensional sheets. The nematic phase molecules are oriented and aligned in a spiral about like a helical axis. This forms like a randomness that makes them less symmetric and thus giving a rise to the anisotropic properties. Chiral nematic LCs or liquid crystals are special cases of nematic liquid crystals that are optically active due to their molecular chirality and distinctive twisted structure. So liquid crystal exhibits metallic mesophases at lower temperature and can either reversibly transition into a crystalline solid, isotopic liquid, or other mesophilic structures, nematic or cholesteric, with temperature variations. There are two types of transitions. Ni transition gives a sudden color change at a target temperature, which can either be reverted upon cooling or give a pseudo irreversible color change if the alignment displacement occurs. NS transition gives a constant color change from the blue to red end of the spectrum to black infrared section as the pitch lengthens with decrease in temperature. And the last one is the VO2, thermochromic vanadium oxide. VO2 thin films have been used in conjunction with photocatalytic TiO2 in the production of smart windows. The transmittance of VO2 is relatively high and constant in the visible range until it is heated above its transition temperature, TC, at which its transmittance in the infrared region decreases significantly. At low temperatures, VO2 exists in a body-centered cubic monoclinic form, which consists of a tilted octahedral lattice structure with the vanadium atoms in the center. At 68 degrees, VO2 undergoes a phase transition to a rutile, tetragonal, or metal-like domain structure that is highly reflective with the ability to regulate solar heat flux by responding to temperature automatically. So here are some application of the thermochromic materials. The first one is smart textile and clothing. So the textile industry testify the operation of new materials distinguished by their thermochromic character, permitting the production of personalized products. These materials are applied in the production of pants, t-shirts, swimming suits, work clothes, curtains, and some toys. For instance, the Japanese company Toray developed thermochromic fibers able to show approximately 8 different colors in the temperature range from -40 to 80 degrees. So as you can see in the picture below, there's a man wearing a shirt. It is actually a blue shirt, and the red part of the shirt are the changes in color when it is subjected to heat. So after you work out, your body heat is increasing, and then your shirt will change color. This is one of the use of the thermochromic materials in clothing. Second one is temperature sensors and indicators. So in order to determine the reaction heat in the chemical reaction and temperature variation, temperature distribution measurements of chemical heating apparatus, the thermochromic materials are widely applied as temperature indicators for warning and monitoring of temperature in industrial and daily life. Besides, the thermochromic materials have pierced people's daily life as an effective temperature indicator and have been applied in order to indicate temperature of frozen foods. Baby spoon, they change color quickly if the food is very hot. In addition, thermochromic materials could be applied in the medical field to indicate temperature in therapeutic process. For example, in transportation field, they might be applied to warn explosion dangers of overheated tires. The example that I'm giving is the baby spoon. So when the spoon carries food that is too hot, the color of the top of the what's called the front of the spoon will change. So it will indicate the feeder of the baby that this food is the temperature is not suitable for the baby. There are also architectural applications. So one of them is the thermochromic coating for intelligent glazing. So thermochromic glazing is a type of intelligent glazing where the properties of the glazing changes according to some external stimuli. More particularly, a thermochromic window is a device that changes in transmission and the reflectance properties at a critical temperature, TC. At this specific temperature, the material undergoes a semiconductor to metal transition. At temperature lower than the TC, the window lets off the solar energy, let it through, and the temperature of the TC, the window reflects the infrared portion of the solar energy. In such a way of thermochromic windows may help to reduce air conditioning and heating costs, leading to a more energy efficient buildings. Intelligent thermochromic glass can be made, which can switch at temperatures that are particularly important, 25 to 30 degrees, and that the precise switching temperature could be chosen by a level of tungsten doping. These coating were made by a process compatible with an currently used in commercial glass manufacture, APCVD. Next one is smart windows. So smart windows is almost similar to the previous. So smart windows are windows that help to filter undesirable solar radiation. They are typically used in buildings that are designed to be more conscious of climate change. The thermochromic materials are an important aspect of creating the smart windows as they facilitated energy efficiency in these buildings. They are capable of this functionality by regulating temperature during different seasons by trapping heat during the colder months and decreasing it in the warmer months. This is usually accomplished by the changing optical properties of these thermochromic materials-based devices, namely reflectance and transmittance. The thin film thermochromic material used in these applications is usually in its cold state. This implies that it reacts like a semiconductor, making it less reflective in the near infrared radiation. However, this material changes its structure from monoclinic to rutile as temperature increases. This transition is known as a semiconductor to metal transition, or vice versa, as it begins to act like a semi-metal reflecting more solar radiation in this state. So it's similar to the thermochromic coating for intelligent glazing, but this is coating. And this is a recent advances that I found of the thermochromic materials. A green thermochromic material are of great interest in many applications. Thermochromic and phase changes materials are commonly used as a smart device to facilitate temperature sensing and passive heating or cooling systems, respectively. Since most of the current thermochromic materials are non-degradable, toxic, and or non-green, there is a great opportunity to develop a greener material with high performance considering the wide range of materials that can exhibit thermochromism. Green thermochromic material uses a thorough understanding of mechanistic pathways of this phenomenon in materials and the constituent requirements of green materials, such that new system can be designed using non-toxic, bio-based, and or biodegradable materials. So the challenges in working with thermochromic materials is the limited temperature range. So the temperature range is not that wide. It differs for every material, and the cost effectiveness, the toxicity concerns, and the environmental impact. And for the innovations of the thermochromic materials is the encapsulation technique, the bio-based and sustainable materials, multi-responsive materials, and also advanced manufacturing techniques. That's it for my presentation. Thank you very much.